Okay, today we are going to compare the bonding in oxygen and carbon so that we can explore a different type of covalent bonding. And I'm using oxygen and carbon, okay, because they're both nonmetals. So when they're present as elements, the only bonds you're going to have is covalent bonds. So if I've just got oxygen by itself, I've got bonds between nonmetals, which are covalent. And if I've just got carbon by itself as an element, I will just have covalent bonds between the nonmetal carbon atoms. So they've got similar bonding, but as we can see, very different properties. Oxygen is a gas at room temperature, which must mean there are weak forces. Carbon is a solid at room temperature, which means there are strong forces, yet we're saying in both cases that they are covalent. So if we have a look at what's actually happening here, okay, if I had a beaker of oxygen, and let's just say I had 100 oxygen atoms, what would happen is that the oxygen atoms all pair up to form O2 molecules. And that's what I call each of those O2s. I call it a molecule. And there's only 2 atoms in each of my molecules. Over here though, with carbon, I don't form small molecules. Every single carbon atom in my beaker joins together to form one large continuous structure. Okay, so the carbon atoms all bond together to form one big thing, whereas over here, the oxygen atoms pair up to form small individual molecules. And that's what's going to classify their bonding, okay? Because oxygen is forming molecules, I can say its bonding is simple molecular, or I can call it simple covalent. Whereas over here, because I form one big giant structure, I say that it's giant covalent. All right, so we've got 2 different types of covalent bonding. In one, all the atoms just join together and form something giant. In the other type, and this type is more common, the atoms either pair up or form small groups. You could have CH4 or H2O. They form small groups of atoms called molecules. And how exactly does this affect their properties? All right. Well, if you've got something that's simple covalent, the melting point and boiling point is low. So they're typically liquids and gases at room temperature. If you've got something that's giant covalent, the melting and boiling points are going to be high. And we've seen before that melting and boiling points depend on the strength of forces, all right? Because over here I'm forming molecules, all right? I'm just going to put a circle around each of these O2s. Each of these represent a molecule, and between molecules I've got intermolecular forces. So there's a force between those 2 O2s, there's a force between those, force between those. All right, all of these molecules are attracted to each other by what we call weak intermolecular forces. And when you're trying to melt or boil oxygen, okay, they're the forces that are break. There are strong covalent bonds holding the 2 oxygen atoms together, but because we also have weak forces present, when you melt or boil it, it's the weak forces that are going to break, and they don't require much energy. Over here, I don't have any molecules. There are no molecules if it's giant covalent. It's just one big thing. And if there's no molecules, then you don't have any weak intermolecular forces. All you have are the really strong covalent bonds. So you try and melt or boil this, there's no weak forces to break. All you've got are strong forces, and they are incredibly hard to break, and that's why it requires lots of energy. Okay, so the formation of molecules means you've got weak intermolecular forces. They're the forces that break when you melt or boil. Without the formation of molecules, you do not have weak intermolecular forces. You only have strong covalent bonds. That will require lots and lots of energy to overcome. Other property, all right, if you're talking about electricity, there are exceptions to this, but in general, for simple molecules and for giant covalent, we just say no, they don't. And the reason is the same for both. We say that they have no free moving charged particles. Okay, so for both of them, in general, although there are exceptions, they don't. No free moving charged particles. Now you might ask, well, how are you supposed to know if a covalent substance is giant or simple? Most of them are simple. Okay, most of them will be simple. There are only a few that are giant, and ultimately you just have to learn them. So if I come over here, these are the ones that are giant, all right? So carbon comes in a number of different forms called the allotropes of carbon. Diamond, graphite, graphene, and carbon nanotubes. There is another one called Buckminster fullerene, but Buckminster fullerene is a molecule. These 4 allotropes of carbon however, are joint. So all of these allotropes of carbon are joint. You've also got the element boron in group 3. You've got the element silicon, which is just below carbon in group 4. And then when silicon reacts with oxygen, it forms silicon dioxide, SiO2, and that is also joint. That one's confusing because the formula makes it look small, but this formula is just a ratio. It tells you for every silicon, there are 2 oxygens, but you could have 1 million silicons and 2 million oxygens all joined together in this large structure. So these are the joint ones, okay? And remember, if they're joint covalent, your properties for every single one of them, you are going to say that they have a high melting point. For every single one of them, you're going to say that there are strong covalent bonds which require lots of energy to overcome. The other property, electricity, little bit trickier because there are exceptions. So in general, we say joint do not conduct electricity, but these 3 I've highlighted here do, and you need to be able to explain why. So they're all allotropes of carbon. In diamond, your carbon atoms form 4 bonds. So carbon has got 4 outer electrons, and in diamond, all of those electrons are used to form covalent bonds. But in graphite, graphene and carbon nanotubes, carbon still has 4 outer electrons, but this time carbon only forms 3 bonds, meaning each carbon atom has got 1 electron left over. And this electron becomes delocalized, and that means it can move around. It doesn't have to stay in carbon's outer shell, it can move around. And because electrons are charged, you now have a free moving charged particle which can carry current. Okay, now the other joints don't have this. These guys are exceptions, and it's because carbon is forming 3 bonds instead of 4, giving them a delocalized electron to carry current.